Last time, we introduced the piecewise cubic spline as a way to smoothly interpolate between data points. This is very useful on data from Runge's function, for example. Whereas the polynomial will pass exactly through the supplied data points, normal interpolation of the entire range will result in wild oscillations between those data points. This color-coded picture shows how we split Runge's function into 6 equally spaced segments. Remember that each of those segments has its own third-order polynomial that interpolates between two endpoints. For example, f0, seen in red, is a cubic that connects y0 and y1. f1, seen in orange, is a cubic that connects y1 and y2, and so on and so forth. Also remember that t ranges from 0 to 1 for each segment. That can be seen in the data table on the previous page. That leads us to the next observation. The right endpoint of one segment must be exactly equal to the left endpoint of the next segment. For example, the right endpoint of f0 must equal the left endpoint of f1. The same rule applies at the junction between every other pair of segments. This is necessary if we want a single continuous curve when we join all the segments back together. In fact, that is the whole idea behind the piecewise cubic spline. Split the original data set into a bunch of smaller segments, cubic interpolate each one of those segments, and then join the segments back together to have one continuous curve. The continuity of data position can be seen on the first graph I showed. Notice that each colored segment connects to its neighbor without any gaps. So what about these guys on the bottom? Those represent continuity of slope. Not only must two functions meet in the same position at their boundary, they must also have the same slope. If this condition was not imposed, we could get kinks when we join the segments back together. We want a smooth transition from one segment to another, so we impose this condition. So why did I label them D? Perhaps because slope is expressed as a derivative, D for derivative. Regardless, the particular symbol used isn't as important as consistently using the same symbol. I could have called them K or P or Q or whatever. Let's just stick with D. Whereas we know the Y values above, we do not know these D values yet. Just hang on and we'll see how to solve for them. The continuity of slope can be seen on this graph. Each colored line represents the same slope between any two adjacent segments. At the top of this page, we see the general form of an interpolating cubic for any given segment. Below that is the general form of the derivative. The derivative is found quite simply by employing the power rule of differentiation, term by term. The bottom 4 lines show what happens when we evaluate the function and its derivative at its left and right endpoints. It should be noted the left endpoint corresponds to t equals 0 and the right endpoint t equals 1. Just from that, we have already solved for the coefficients a and b in terms of y and d. To solve for c, we must do a bit of algebra. Simply subtract 2 equations from the previous screen, substitute what we already know, and clean it up a bit. C is solved for in terms of y and d on the very last line. To solve for d, in a similar manner we substitute what we already know, gather like terms, and clean up a bit. D is solved for in terms of y and d in the last line. Don't confuse little d with big D. Little d is the coefficient in our cubic. Big D is the slope at the endpoints of that cubic. We have seen continuity of position and continuity of slope. The final condition we impose is continuity of curvature. Curvature is related to the second derivative, hence f double prime. The curvature at the right endpoint of f0 must equal the curvature at the left endpoint of f1. Same for the boundary between other segments. Continuity of curvature also ensures a smooth transition between segments. Notice that the left endpoint of f0 and right endpoint of f5 are equal to 0. These are the absolute endpoints of our original data, so there are no adjacent segments. The third line shows the second derivative of our cubic for any segment. That is done by using the power rule of differentiation term by term on the first derivative. The last two lines on the bottom show what happens when we evaluate the second derivative at its left and right endpoints. Let us begin with the absolute left endpoint. This comes from the first line, 2 slides back. Then we just substitute for f0 double prime and c. Carrying out the algebra and cleaning things up a bit leaves us with the expression in the final line. Things get a little more involved when we equate the endpoints of adjacent segments, but not too much. It's still a matter of substitution, collecting like terms, and cleaning things up. I've used color coordination to help you see which terms combine together and which ones cancel out. Here I have shown the process specifically for f0 and f1. The same process can be applied to each other pair of adjacent segments. I omit the details and instead leave a summary of the results here. Feel free to verify a couple of these for yourself. It will do much to enhance your understanding of this derivation. Lastly, we must set the second derivative of the absolute right endpoint equal to 0. Substitute, collect like terms, and simplify. Because there are a few more terms involved than the left endpoint, I've included color coordination to guide your eyes. In this single slide, I have consolidated the results of the past few slides. You may be asking where all of this is going. Hold on, we are almost there. Notice that we have 7 equations and 7 unknowns. d0 through d6 are all unknown, but we know all the y values. Furthermore, these are linear, so we can represent them as a matrix. The matrix form is seen here. That sets us up to solve for each d. Then the d's and y's are used to evaluate the coefficients of our cubic for each segment. If you'd like to see the details of that calculation and what the numerical solution is, check out part 1 of this lesson. I wanted to focus on where this expression comes from and how it can be applied more generally to any number of segments. My derivation was based on 6 equally spaced segments, but this matrix can certainly be enlarged to accommodate any number of segments. Just follow the same pattern. 4s all along the main diagonal, except 2s in the upper left and lower right. All 1s in the diagonal above and below the main diagonal. 0s everywhere else. This is called a tridiagonal matrix. The d vector should be extended to match the number of rows in the matrix. Regarding the y vector, notice the uniqueness of the first and last row. They have a difference between adjacent y's, y1 minus y0, and y6 minus y5. Every other row skips the adjacent y, y2 minus y0, y3 minus y1, y4 minus y2, etc., etc. Just be mindful of that when you set up a cubic spline of your own. One last thought before we conclude. You may be asking why we used a cubic instead of linear or quadratic interpolation. Well, take a look at this graph. It is quite obvious that piecewise linear interpolation maintains continuity of data position between adjacent segments. That is, there are no gaps between neighboring segments. However, there is no continuity of slope. That is why we have abrupt kinks between segments, rather than a smooth transition. Quadratic interpolation would add another coefficient, and that would allow us to impose continuity of slope as well, which would give us a better fit than linear. I omit the details of that here. That would require another full-length lesson to develop. I just wanted to point out that first order, linear, interpolation allows us to impose one constraint, continuity of data position. A second order allows 2 constraints, continuity of position and slope. Third order allows 3 constraints, continuity of position, slope, and curvature. Each time we get a slightly better fit to the data. There is quite a bit of information to digest in this lesson. This is one of those things you might have to watch a few times for it to sink in. I highly recommend you watch the first part of this lesson if you already haven't. That could clear things up a bit too. Otherwise, feel free to post any remaining questions you may have in the comment section below. There's certainly a lot that can be discussed pertaining to this topic.